Talking about local coordinates. And I mean, today is sort of the awkward middle lecture where last time I could introduce and prove a classical theorem. Like today I'm trying to give you a perspective on context for a new result, and then tomorrow will be very self-contained because it'll just be a proof of a theorem. But for that, we needed to know the definition of semi-conjugacy, what to think about this space, like how this fits into a big picture. So all of this kind of bits and pieces work I have to do today. Okay, so let's talk about coordinates. And the theme of today was analogies between linear representations, like what Goldman studied, or what Milner was doing, and this space of foliated circle bundles, and kind of a miracle that there's some analogies between the two. So I want to start by motivating coordinates on this by talking about coordinates on classical linear representation spaces. So if you have, so now gamma can be any discrete group, or maybe a finitely generated group would be a good one to think about. It's sort of a well-known old fact that the character space for gamma representations into SL2C can be given coordinates using traces of elements, or characters if you're in SLNC. Okay, so why trace? Trace captures some dynamics. Okay, that's a nice property. But the property that we need is that it's a continuous and conjugation invariant function. Right? So that means the fact that it's continuous means that it's actually invariant on the closure of conjugacy classes. So it defines a function on the character space. Okay. And if you have a finally generated group, it's a fact that you can prove using trace identities in SL2C that a representation is determined by the trace of finitely many elements. Okay? So my example from before, Fricke's result that if you have representations of a free group on two generators, say generated by A and B to SL2C, you can parameterize these exactly with a triple of complex numbers. Okay, by taking a representation, and actually here's the identification. You look at the trace of the image of one generator, of the other generator, and the trace of their product. Okay, all three tuples are possible. This gives you, and this specifies the representation exactly. Okay, so the upshot of this is why I'm using slides for a little bit, is I want to show pictures. Is that these are super nice to work with. Here's a picture of the real points of this variety. Okay, so this is R3 is the empty box, and the surface here is just the level set of a nice function. Here it's the set where the trace of the commutator of the generators is 4. Okay. So this is from a paper of Goldman called The Modular Group Action on Real Characters of a One-Hole Torus. He's studying this representation space and specific transformations of it. Okay, so this is nice to work with. What can we do for the character space of group actions on the circle? So these are semi-conjugacy classes of actions. And I want a function like trace, so some conjugation invariant continuous function on homeomorphisms of the circle. And maybe you know where I'm going with this. Here's the definition we had last time. It's the rotation number. So it works for lifts to the line. You take a homeomorphism of the line that commutes with integer translations. You iterate, you figure out the average distance it moves points over. Okay. And our rotation number on the circle is just this mod z. Okay. So here are two properties that are completely analogous to what we have for trace. It captures some dynamics. So here it's rational if and only if the function back down on the circle has a periodic orbit, or specifically the lifted version is of the form P over Q, if and only if there exists a point on the line so that when I apply F Q times, I get X plus P. Okay. And it's continuous which is sort of special to the line. You can check it from the definition, but it's not like a zero-line immediate thing. It's continuous, and it is immediate from the definition it very quickly follows from this that it's conjugation invariant. And in fact, so that will tell you that it's invariant on the closure of conjugacy classes. You can also check directly that it's semi-conjugacy invariant. Okay, so this gives us a function on the character space. Okay. And you would hope that we could use this to give coordinates, just like trace coordinates. And the miracle is that this is true, at least locally. Okay, so this is theorem of Gis that kind of came out of this whole picture of semi-conjugacy that I was talking about, rephrased in this language by Matsumoto. It says that a representation up to semi-conjugacy is locally determined by knowing all the rotation numbers of elements. Okay, you don't need finitely many, you need all. No finite set is good enough. Locally means that there's a neighborhood of this representation where the rotation number is completely determinate. You don't say in a neighborhood, just knowing rotation numbers isn't quite good enough, but it's pretty close. So I'll show you the global version uses lifts to the line and comparisons of rotation numbers and products. Okay, so this is a 2 cocycle. It's close to what we're using to define the Euler class, actually. These are all quite interrelated. But if you don't want to lift things, you at least get a local theorem. Okay, so the upshot of this is I can use these coordinates to study the space that we want. So let's compare. This whole thing is very optimistic. It's like, great, I have coordinates on a space I'm interested in. Let's draw a picture of the space and coordinates. And here's the pessimistic side. It's a lot more complicated. So let's do a side-by-side comparison. So here I have the character space for free groups into SL2C. Actually, that surface shouldn't be there. If I look at the whole thing, it's just like the empty box, three-dimensional complex space. And you might ask, what happens if instead I have a representation of the free group on 2 generators to homeo of the circle? And I just really want to understand, what's instead of the triple trace row of A, trace row of B, trace row A and B, if row goes from F2 generated by A and B, let's use a better marker, to homeo of the circle, like what are the possible values of rotation number of like row of A, comma, rotation number row of B, comma, rotation number row of their product. All right, here it's box. Here it should be some triple of R mod Z valued numbers. It looks like this. Okay, so that I'm going to prove in a second that this is the right picture. At least I'll give you a hint at how you prove it. Yeah, it has this kind of weird self-similarity thing going on. So this is actually like a 3-dimensional plot of it where you take, here going from 0 to 1 is the rotation number of A, from 0 to 1 is rotation number of B, and the height is giving you the maximum value of the rotation number of their product. And anything in between can be filled, can be attained. Okay. You might ask about these corners. This function is like, what does that mean? Upper semi-continuous, where these surfaces, like these flat regions, are closed. Okay. So there's a sharp drop off here. Okay, so it's a little messier. Let's do another comparison. I had this nice level set of a surface that was like an algebraic curve. You might ask, like, what does the trace of a commutator look like? What does a rotation number of a commutator look like? Here's the correspond. This is again not just a computer experiment, but provable that this is the right picture. This is called a ziggurat because This picture looks, I guess, kind of like a ziggurat, like one of those temple things. This one does not so much. But so the level set would be like a slice of this. So it would be totally disconnected. This has spikes at all irrational points of height corresponding to the denominator. Yeah, maybe one more picture. So Caligari and Walker in this paper have an algorithmic approach that if you give me any word in the generators but not their inverses, you can draw this picture. Okay, so this is a basic kind of dynamical question to ask, like what are the constraints on rotation numbers, given rotation numbers of two homeomorphisms of the circle? If I compose them in some way, like what does the dynamics of the composition look like? So they can solve this completely by an algorithm as long as you don't see inverses, and if you do see inverses, like actually their algorithm is stuck. This is the commutator case is the only thing that they can do. I think they're kind of waiting for someone else to sort of take up this question. It's very approachable. You can sort of start to run computer experiments to see what can happen. But I think there's sort of some fruitful work to be done there. Okay. So what I want to finish with today is I want to prove, because it gives you a kind of a nice sense of how to work with these things. I want to talk about the proof of why this picture is accurate. Okay. So I'll leave that up there and we'll just do the proof. Okay. Yeah. So. This is a nice thing to finish with because it will give us a practice sort of doing a hands-on argument on the circle. And let me give you a theorem that says this picture is correct. Okay. So the general program is, in some sense, to draw slices of this character space in coordinates. Or in other words, given the rotation number of some homeomorphism, which you're thinking of as like the image of some group action, maybe two of them, and a word in F and G. So so maybe two generators and another element of your group. Maybe a word is W. What are the possible values of the rotation number of W? Okay. If you ask this for traces of matrices, if I know the trace of a matrix and the trace of another matrix, and I take some big composition of them, A, B, A, B, whatever, it's a completely answered question that was known quite a while ago, and it's kind of central to understanding trace identities in SL2C. But we understand it for general linear groups. Okay, so the theorem is that as long as there are no inverses in the word, there's an algorithm that does it for you. But a special case of this, where the answer, the output, has a closed form, okay, is that if I specify this to be one number and that to be another number, and my word is here, it's just the composition of the two of them, A, B, or in this language, F, G, you get this picture. Okay, so there is a closed form for the maximum possible value of the rotation number of F composed with G. Okay, given the constraint that the rotation number of F is S, and the rotation number of G is something else, say T. Okay, and the form of this is the following. Okay, it is the supremum of some rational number, okay, where P1 over Q is bounded by S and P2 over Q is bounded by T. So it's the supremum over all rational numbers below S and T with the same denominators of this fraction. Okay, that is the graph of this function. Okay. Let's do a quick example that we're going to prove. Actually, I'm going to do proof of an example, but my example proof will be running the algorithm in an easy case where we can just do it by hand. Okay, so let's figure out what the example, so let's suppose S is a half and T is a half. Okay, so the answer I'm supposed to get here, okay, so I'm supposed to get, let's see, if I want to maximize this, I should take the smallest denominator possible, and I'm already given that. It's a half and a half, right? So I should actually plug in 1/2 here and 1/2 here. So I should get 1 plus 1 plus 1 over 2, that's 3 halves. And actually, that's the height of this point here. So it's exactly that one. Okay, so I've been writing rotation numbers, but this is all, like always, when we want to figure out how many times we've gone around, this all happens on the line, and you can take everything mod z if you want to understand it on the circle. Yep. I don't like decorating everything because I always forget. Okay, let me tell you how you would compute this. Okay, in a very sort of, you know, the beauty is this is just a very naive, simplistic thing. Okay, so let's show we're going to get what you're supposed to get. What I've got on the circle is I've got F and G both have rotation number 1/2. So that means that they have periodic points of period 2. Right? So I know there's some point here where under F it goes to some other point, and then if I iterate F again, it comes back. Okay. And I know G similarly has a periodic point of period 2. Okay. And that's all the data I have. In fact, I don't even know that these are linked, right? The 2 periodic points of G could be over here. Do not know. But you'll check each possible arrangement at a time. So I'm trying to understand what happens if I, you know, take a point like this and I apply F, and then I apply G, and then I apply F, and then I apply G, and then if this is 3 halves, if and only if, right, there exists some point X in the line, such that if I do F composed with G, or F composed with G, was what I was writing, 2 times, I get X plus 3. Okay, so this is what I'm trying to look for. And I don't know anything about what F and G are specifically. I'm trying to say that at most, this can happen. Okay, so I can't get anything bigger than this. Right? And this max thing actually means that this is part of the theorem. It is attained by some examples. F and G. Okay, so let's show that you can't do better than this number. All right. Okay, so here's the line. Here's my integer point, so I'll quotient to being the circle. Okay. Give myself lots of space. And I have some periodic points of F. Maybe they're like this. Okay, so F is moving each one of these points along to the next one. Okay, so this is X, there's F of X. And G has periodic points, and let's suppose it'll only depend, the answer I get will, or the algorithm I run will only depend on whether these are linked or not. Let's suppose it's like my picture there for the moment, and they are linked. So here's periodic points of G in hardly visible red. Okay. And let's suppose I had two homeomorphisms of the line that satisfied these constraints. Anything satisfying these constraints. So all I know is that f takes one of these points to the next one over. Oh, thanks. Great. You'll actually be able to see. Yep, 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 yep. All right. I'm trying to maximize the distance a point moves under f composed with g squared. Okay. So let's start with, so remember G is doing this to the points, but in between it could do anything else. All I know is it takes this interval to that interval. Okay. But let's start with this point here. Okay, this could be my x. And I apply G and I go exactly to this point. So here's G of x. All right. What's the best that f could do? F is supposed to take this interval to that interval. Okay? It could do it in some not isometric way so that this middle point was squished really close to the end. Okay, so the best I could do with f is to go close to the end here, but not exactly. Okay. Let's apply G then f again and see what happens. So if I apply G, G is supposed to take this interval here. Oops, sorry, I got this one confused. F takes this interval to that interval. So I'm allowed to move points in the interior close to the end of there. I just drew this in the wrong place. Boop. Okay. G is supposed to take... I keep landing in the wrong place. It's like I'm bad at throwing. There we go. Boop. All right, G is supposed to take this interval to that interval. The best it could do to a point would be to move it all the way over to here. Okay, so G, F, G, and then F, same argument, supposed to take this guy to that guy. The best it can do to here. And we've arrived at a point which is, there is x, there's x plus 1, x plus 2, less than x plus 3. Okay, so even if G and F are trying their hardest, okay, there exists some point x such that, so no matter what, if the periodic points of this configuration, there always exists some point x such that G composed with f squared of x is strictly less than x plus 3. Okay. Okay. So although I was sort of doing some hand waving and be like, G can at most do this, this can be completely formalized. That is the argument. Okay. And moreover, if you started not at this point, but say at something that was not a periodic point for G, and you made them have these kind of strong dynamics that push things hard to the right, you can construct an example. Okay. So you can specify F and G on the nose with some point y such that f composed with g squared of y is at least x plus 3. Okay. Okay, so there must be, by like intermediate value theorem, there must be something that gets translated exactly 3. Okay, so you can, this means that you can specify f and g so that some point satisfies this. Okay, but no matter what you do, there'll always be some point that does not make it that far. Okay, that's what proves that this maximum is a maximum. Okay, and then you run the same argument for the other configuration. So if my periodic points look like this and like this, you try and run the same argument, and actually you can't even achieve this bound. You'll only do worse. You actually get a lower maximum value. I think you get something like 1, maybe? I'm not sure. Okay. But that's something you can just do by hands. Okay, so now you know their algorithm. What the algorithm does is it works on rational points and then argues for general reasons that this is like an upper semi-continuous function, and so you just need to know its values on rational points. Okay. You look at rational values only, and a rational value means you have periodic points. You enumerate all possible combinatorial configurations of the periodic points of f and g. Here we had 2, linked and unlinked, but in general you might have 100. And you imagine what would happen if your functions were trying their hardest to move points to the right, to make your rotation number as maximum possible. And this is really kind of a discrete thing, right? We actually were saying that G moves things like F moves things in an interval, basically up to this point, but not equal to it. Okay, so that's really a discretized process where you're saying intervals are associated to points. Okay, and then you iterate and you figure out how far points go under these kind of extreme maps that take intervals to points, and you check the bound. Okay, and you argue that whatever the best bound you get can be achieved by specific maps. Mm-hmm. And that's the argument, and that's the algorithm that produces all of these pictures. Okay, so I think that's a good stopping place for today. This is a fun paper to read if you're interested, and I think there's lots of unanswered questions, and also like the basic argument is pretty hands-on. Next time I'm going to use all of the tools that I have secretly been sort of building up for us: rotation number, Euler number, this idea of spaces of action, to prove this sort of a doable case of this rigidity theorem that says if you have an isolated point, then it comes from a magical representation basically into PSL2R. But that's for tomorrow, so we'll stop now today.